Hi folks, and welcome to this Friday lecture. And today we're going to wrap up part 1 of this lecture that is called Performance of Computer Programs. So last time we talked a lot about parallel algorithms and we looked into a lot of theory. And it was our aim to devise a machinery, and in particular a machine model, that allows us to assess the work complexity and the time complexity of computer programs separately. For that we first devised the PRAM machine model, and based off of that we later found the way simpler work time paradigm, and we already discussed a couple of parallel algorithms. Like we discussed the Zaxby parallel algorithm, which we found was embarrassingly parallel, and we also discussed the algorithm parallel reduction, which we found to not be embarrassingly parallel because it is an iterative algorithm in the sense that we perform log n iterations, and during each iteration we have to halve the number of processes that participate in the calculation. Nevertheless, we found that this algorithm is work efficient, so as we are performing the same number of operations that the best known serial algorithm would perform. Today we're gonna wrap up things by having a look at yet another parallel algorithm before we finally recapitulate what we learned in this first part of the lecture, and then we will have a very first look into computer graphics. So in the algorithm pointer jumping, the input to the algorithm pointer jumping is a forest of rooted trees. And what does that mean? Rooted trees are characterized by, each node in a rooted tree is characterized by its predecessor. So each node in the tree stores a pointer to its predecessor, and the root node is its own predecessor. Yeah? And with the algorithm pointer jumping, it is our objective to, for each tree in the forest, find the root node. So the forest, that is the input to our algorithm pointer jumping, is given as a predecessor list, and the predecessor list stores for each node in the forest its immediate predecessor. Like, consider the forest that I depict down here, and this is the predecessor list for this forest. Yeah, like the root node of each tree is characterized by that the predecessor is the node itself, and as you can see, the predecessor of the root node of the first tree is the node with the number 0, and the root node of the second tree is node number 8, and it's also its own predecessor. And then you can see, like, the predecessor of 1 is the root node of the first tree, is 0, and then the predecessor of 6 is node number 1, and so forth. So this is the input to our algorithm. Is a forest of rooted trees in the form of a predecessor list of length n, and the output of our algorithm is a list S of length n, so that every entry in I is j if and only if j is the root of the tree that I belongs to. So what we're after is for each node in the forest, we want to know what the root of that node is. And therefore we transform this given predecessor list into a list of only the root nodes. And this is what an implementation of the algorithm pointer jumping would look like. And we would just run a parallel for loop over all entries in the input array. And then first off, we would just initialize the result array with just the entry from the predecessor list. So and then we would, in a loop, we would assign to that entry the predecessor of the predecessor. So, and we would do that iteratively, and by that we would basically climb up the tree until we were at the root. And when we were at the root, we can find that out easily, because when we're at the root, then the predecessor of the predecessor is also the predecessor. And that is our stopping criterion, and then we know that we can end the iteration. And until we are there, we just assign the predecessor of the predecessor. Yeah, let us just have a look at how that looks in practice. And here I'm depicting our algorithm again, where we have the parallel for loop, and then the assignment at the beginning, and then we have this loop that is performed for all the I entries on the list. And let's just consider this example here with those two trees. Like we have this one tree that corresponds to this part of the predecessor list, and then we have the second tree in the forest that corresponds to the upper part of the predecessor list. Like we can see like that the predecessor of, for example, node number 1 is 0, and the predecessor of node number 7 is 0. And we can also see this in the predecessor list, and we also see that the root nodes have themselves as their predecessors. So, and then in the first loop iteration that is performed by all I in lockstep, we just assign the predecessor of the predecessor. Yeah, and for the first entries, this is actually easy. Like the predecessor of the predecessor is the predecessor itself for the root, so we just assign 0. And for node number 1, we see that the predecessor of the predecessor is the root node, so it's 0 again. And for node number 2, we see that the predecessor of the predecessor, so the predecessor of node number 1 is node number 0 is the root again, so we assign that. And then for node number 3, we see that the predecessor of the predecessor is node number 1. And then again, we see for node number 4 that the immediate predecessor is 3, and the predecessor of 3 is 2. And for node number 5, we see that the immediate predecessor is 2, and the predecessor of 2 is 1. And I mean, I think you're getting the hang of this, so I'll just skip through. This is done for the this is the result for the other tree, right? And let's have a look at how this looks when we adapt the trees accordingly. Like what we can see is just that the predecessors were basically replaced with the second order predecessors after the first iteration, right? So and then we perform the second iteration, and the second iteration basically, so I'll just show you the result of the second iteration, because I think you understand how the mechanics of this work. Again, what I want to point you to, or what is significant, is the fact, and this is easy to illustrate for node number 4 here in the first tree, is this is the a predecessor relationship that was valid during the after the first iteration, right? Where the predecessor of node number 4 was node number 2, right? The updated predecessor. So the predecessor of node number 2 was the second order predecessor. So the intuition would now kind of prescribe that we, in the next iteration, assign the third order predecessor. And this is actually not the case because of how the whole thing is implemented. Like, as we are always assigning the predecessor of the predecessor, we are now actually assigning the fourth order predecessor, that is the root node. And because of that, because the order of the predecessor that we're assigning doubles with each iteration, we know that the time complexity, the number of parallel steps taken, is logarithmic. And even more, we know that the number of time steps taken by the algorithm is logarithmic in the height of the deepest tree, which in this case happens to be the green, the tree that is in the lower half of the predecessor list. Yeah, and for those who aren't so fond of my handwriting, here are also 2 slides that show the whole procedure again with the 2 iterations, and also with the graphs and the pointers to the predecessors, etc. And with that, you should have enough material at hand in order to comprehend this example and this algorithm. And let us now briefly discuss the complexity of the algorithm. Like we already said, that the number of loop iterations of the while loop is logarithmic. During the first iteration, all nodes point to their second order or to their second degree predecessor, right? And then we store this intermediate result. We store it in the temporary array, in the array S, and therefore we can reuse it in the next iteration. And for that reason, we will then not choose the third order, the third degree predecessor, but the fourth degree predecessor. So if there was a next iteration, which in our case there wasn't, then we would instead choose the 8th degree predecessor and so on. So the time complexity is O of log h, and h is the height of the deepest tree. And as we're having a parallel for loop that runs over n items, so over the size of the array, the work complexity is O of n dot log h. And then the algorithm is a CREW PRAM algorithm. That is, it requires concurrent read capabilities. It's easy to comprehend that. Whenever we write something, the write accesses are to the very memory address that the thread or that the parallel work item is assigned to. Whenever we write to exactly this memory address I. So when we read from memory, there can potentially be collisions. We already see that there can potentially be collisions because of this indirection, because it's kind of hard to resolve those indirections. But we know that there are potential collisions because we know that there are certain nodes that have the same predecessor. And only because of that there are collisions with respect to reads, and because of that we need a CREW, so a concurrent read and an exclusive write PRAM. So we will talk about pointer jumping again during the exercises, and there we will see that you can compute prefix sums using pointer jumping. You can compute prefix sums in parallel. And I mean, I can already tease out that pointer jumping might not be the very best algorithm that is out there to compute prefix sums, but we will learn more about that in the exercises. So allow me some closing remarks on the PRAM and work time paradigm models. So the PRAM and work time model are very simple models that help us to assess the complexity of parallel algorithms. But as it is often the case with very simple models, in certain cases those models might actually be too simple for what we're after, like they are idealized models. And certain assumptions that those models make, like for example that memory access latency is one time unit and that there's an unlimited number of processors, for example, might just not be realistic, or might be misleading when we base our judgment only on those models. There's also a word that I want to say about this competing memory accesses. Like in the real world, those competing memory accesses are what makes parallel programs complicated. When we are able to design programs in a way that there is just no contention, then this is good. We should in the first place try to design our algorithm in a way that there is no contention. And those models, like PRAM or work time, help a lot with the reasoning about that. When we, in the first place, try to design an algorithm that is EREW, that is very helpful because this ensures that there is no contention. If there is contention, things become much more complicated. Then those simple models oversimplify a lot. Those models basically just abstract away all the synchronization that is necessary in the real world. And the synchronization part is actually what makes things difficult. And also, when we synchronize, this usually leads to significant bottlenecks. Whenever we enter a critical section, inside that critical section, code basically runs serially, and in addition we have communication overhead and potential wait times. When an algorithm is dominated by critical sections, this is really bad, and in the PRAM model, those really just manifest as ordinary memory accesses, And that tiny remark that our algorithm requires a CREW PRAM and not an EREW PRAM. So it's really important to watch out for those competing memory accesses, and those are what can make programs really slow. So, and with that, we have arrived at the end of part 1. So we really learned a lot. Like, we learned about Moore's law, and we learned about Dennett scaling. And then we learned about that the hardware vendors ran into something that's called the power wall, like the red brick wall. And as a consequence of that, architectures tend to become more parallel. Architectures also become more hierarchical and more complicated. We learned what performance is, and we learned that performance is the CPU execution time, and we learned that the CPU execution time depends on the number of instructions and on the average clocks per instruction, and then on the clock frequency. And we pretty much learned that the choice of algorithms and of high-level programming languages and compilers very much influences the number of instructions and influences the average instruction clocks. We also learned that there are different types of memory, and in particular there's cheap but slow memory, and there is expensive but fast memory. So the vendors tend to devote or to build more of that slow but cheap memory into the systems. And then certain memory regions that are called caches are constructed off of static memory. And therefore we get memory hierarchies, and programmers have to be aware of memory hierarchies in order for their programs to be efficient. And we have to be very careful about things like locality and memory access coherency, etc. And then we also learned a lot about parallelism, and that there is a whole spectrum of different types of parallelism. Like at the very lowest level, there's instruction level parallelism, out-of-order execution, hardware and software pipelining. And when we move further to the right of that spectrum, further to where the developer can actually influence things by the way they write their code, then we see SIMD registers and vector operations. We see multi-threading that can be programmed in different ways. And we also see NUMA architectures with complicated memory hierarchies. And we see distributed memory computing. And we see caches and all sorts of things. And then later, when we had an idea where parallelism manifests, we discussed massively parallel architectures, and we discussed instruments to reason about the efficiency of algorithms that run on those architectures. Like, we discussed Amdahl's law. We also discussed efficiency and costs, which are important ratios in order to understand how efficient our algorithms run on a parallel platform. And we also learned about PRAMs and about work time per ratum, which further help us to analyze our algorithm. And we learned that those theoretical constructs are very helpful, but we also learned about certain shortcomings of those constructs, and that we cannot solely depend on analyses that are based on those theoretical constructs. So this closes part 1 of this lecture. So let me briefly go through a bunch of books and papers that are relevant. Like, this is an assortment, and probably the most important book for part 1 is Pedersen and Hennessy, Computer Organization and Design. And this book is actually, this is a very comprehensive, very huge book, and you will find lots of the things that when I talked about registers and about the MIPS architecture, when I talked about caches, when I talked about instructions, and you will find all that in Pedersen and Hennessy, and you will lots of what I talked when I talked about memory and about caches. You will find that in the paper by Ulrich Drepper, and those are two books and papers are actually very helpful, and I definitely encourage you to take a look into those books. Like, this is a standard book on parallel algorithms. There are also other ones that you might consider to have a look into in order to comprehend the PRAM model or work time, Brent's theorem, etc. Yeah, there's a bunch of other papers. I think some of them, like the papers about Moore's law, for instance, I mentioned inline in the course material. So we're now switching gears, and we'll focus our discussion on rendering algorithms. A main motivation for this whole lecture is GPU, so general purpose computation on the GPU, and for that a thorough understanding of GPUs is important, and also a thorough understanding of how GPUs evolved into what they are today is important. And in order to gain that understanding, we need at least a superficial understanding of the rendering algorithms that were implemented by the GPUs in the first place. And this part of the lecture that will focus on computer graphics and rendering algorithms has the main purpose of providing enough understanding so that we can comprehend the development from graphics accelerators that we had like 20 years ago to the general purpose GPUs that high performance computing practitioners use nowadays for their computations. And in order to gain that understanding, we will discuss a number of 3D rendering algorithms. And the focus of this class is not to provide a general and thorough understanding of computer graphics. So this is not a computer graphics lecture. But what I intended was to deliberately pick 3 rendering algorithms that are relevant to the industry. Like we will discuss the rasterization algorithm that is implemented by the GPU's fixed function pipeline. And that an understanding of that algorithm is necessary to understand where things are coming from, like what GPUs were intended to do in the first place. We will then discuss deferred shading, and deferred shading is a relevant algorithm to the gaming industry. Deferred shading is used to render many lights, and in particular, our discussion on deferred shading will show you how people make use of GPUs in order to extend what was already there, what the fixed function pipeline provides. And you will see that people are quite inventive when it comes to extending or to making use of the GPU's fixed function pipeline, and the deferred shading algorithm will exemplify this. We will then also discuss ray tracing, which is a completely different family of algorithms and which is gaining more and more importance nowadays, in particular because vendors like NVIDIA, who are pioneers in this regard, nowadays ship GPUs with dedicated ray tracing hardware. Like ray tracing is was traditionally considered an algorithm that was just too slow for real-time performance. And we will discuss ray tracing, and we will discuss how images can be generated with ray tracing, so that we can understand this special purpose hardware that that NVIDIA and that also other vendors in the future will ship and will integrate into their GPUs. That we will then later also have a short discussion of parallel rendering algorithms, like parallel in the sense that those algorithms can, for example, be used for side-view rendering on large HPC systems or on multi-GPU workstations. We'll start our discussion of rendering algorithms with a quick review of some concepts and definitions. So the basic operation of 3D computer graphics is rendering. So rendering is the process of generating a 2D raster image from a systematic description of certain entities that are placed in 3-dimensional space, like in a virtual 3-dimensional environment. And the overall process of generating those 2D raster images we call rendering. Then we have so-called real-time rendering algorithms, and real-time rendering algorithms are those algorithms that have such a low latency that the human eye perceives transitions between consecutive images as smooth. And what that implies is, on the one hand, that there is a certain frame rate to the rendering algorithm, so the rendering algorithm can output new images at a certain rate. And another important factor is smoothness of that rate, so that the rate at which the algorithm can produce new images doesn't change over time, or doesn't significantly change over time. So another term that we will discuss from time to time is so-called fill rate limitation, and fill rate limitation just means that the runtime of the algorithm is bound to the image resolution, that is, how many raster points the 2D raster image consists of. So when we're talking about rendering algorithms, we will make certain simplifying assumptions. And one of those simplifying assumptions is that we're rendering fully opaque objects that are in a vacuum. Like we're not considering participating media or objects that have like an optical thickness to them. And we will also generally assume that light, when we evaluate light transport, will behave like particles. In particular, we will not concentrate on any wavelength dependency of light. We will also assume that phenomena aren't time dependent. That is, when we integrate a 3D scene and the light transport in that scene, at a certain point in time, we'll assume that this point in time is infinitesimal. We're not integrating over like a very short time period, but really over an infinitesimal time period. And that means that objects at that time t are stationary. So that, for example, means we're not accounting for certain effects like motion blur, where you would have objects moving over time, like averaging their contribution across the single time step that we're integrating for. And those are simplifying assumptions that people usually make for real-time performance. And there's a general tendency that we can observe is that software developers with increasing compute power, they tend to lift those restrictions. Like we're in a real-time scenario, and then whenever we get our additional Moore transistors and additional cores on our GPUs, for instance, then people either try to lift those restrictions, and when they lift those restrictions, that basically means they try to fix the frame rate that we can achieve. Like we agree that we want to achieve a frame rate of 30 frames per second, for instance, and then we fix that frame rate and then lift some of those restrictions. That means that in the rendering industry, with a more of compute power, like more cores, more transistors, what we usually see is an increase in image fidelity while keeping frame rates or processing times. And the governing equation to all that we're going to discuss in the following is the so-called light transport equation, the LTE. And we're going to discuss its very simplest form. That is, we are making certain simplifying assumptions that there's a vacuum that the objects are in, and there's no wavelength or time dependency. And we're really only very briefly discuss the equation to give you a basic understanding of what's going on. Like the light transport equation is actually the topic of an advanced computer graphics topic, and solutions to the light transport equation. We will discuss some solutions to the light transport equation, but a rigorous discussion of the LTE is out of the scope. Yeah, let's just have a look at what's going on there. So this is the light transport equation again. And what we're interested in is we're interested in lighting a surface, and we're interested in the quantity that is called radiance. And this quantity called radiance is denoted L here. Whenever you see an L, that denotes radiance. And radiance depends on two things. Radiance depends on a position, like this position x here. And radiance is also an angular quantity. Like radiance also depends on the direction that radiance is reflected into. So we're assuming that we're interested in the radiance from a certain position x into a certain direction omega o. And whenever you see omegas here, those are unit vectors, okay? So, and in order to compute radiance, we have to do a couple of things. And the first thing that we're going to discuss is the properties of the surface here. And the properties of the surface here are governed by something that is called the BRDF, the bidirectional reflectance distribution function. And the bidirectional reflectance distribution function depends on two vectors, like on two directions. So it depends on two unit vectors on the vector omega o. And we already know that vector omega o, it's the vector of interest, the vector that the light is reflected into, and where we're interested in evaluating radiance for. And then we're also interested, and then there's also a vector omega I that the BRDF depends on. And the vector omega I is the vector of the incoming light direction. And usually with those kinds of models that we're using, this vector omega I is determined statistically. Like we're assuming that we're lighting the surface, and then there's a certain direction that light is coming from, and then we have our direction omega O that light is reflected into, and this relationship is determined by the properties of the surface here, right? So, and we're assuming that the surface can have some roughness to it. Like there are certain materials that are kind of smooth, like mirrors or metallic surfaces are kind of smooth, and other surfaces have a certain roughness to them. Like for example, like a blackboard. Yeah, like certain surfaces are rough, but this roughness, like the granularity of that roughness, is so small that we can only model it statistically. And we model it statistically by adopting so-called microfacet models. Microfacet models are like tiny patches, tiny surface patches, and those surface patches potentially occlude each other. So, and then we have for this position x here that we are at, we have a statistical microfacet distribution, and each of those microfacet distribution is subject to incoming light, and there's like a bunch of for each microfacet and for each position on the microfacet that we only statistically account for, there are incoming light directions. So now in order to determine the light direction, we just average those light directions basically. And this gives us one statistical incoming light direction omega I, and this is only an averaged quantity. This is basically the role of the BRDF. So the BRDF describes the surface property in X, and there are like a bunch of different BRDFs out there. BRDFs can actually be measured, and there are also analytical BRDFs, like for instance for mirror-like surfaces or for very rough surfaces like stone or chalk. And the BRDF helps us to describe the relationship between those two vectors. And it's usually a statistical measure. Like there are certain BRDFs out there with a definitive solution to omega I, like for example, like perfect mirrors. But those models are actually idealized models. So they are oversimplifications. So in general, we have this BRDF that describes the surface, and the BRDF tells us for a given direction of interest, like we're telling the BRDF we want to see how much light is there reflected into direction omega O, and the BRDF will tell us a statistical light direction. It will also tell us the light contribution, so the radiance at this point with regards to the two vectors. So the light transport equation depends on the BRDF. And we now know what the direction vector, the unit direction vector omega I does. And another important fact about the light transport equation is an inherent recursion. Like we are locally computing this BRDF, and the BRDF tells us local radiance, and the BRDF also tells us an incoming light direction, and this incoming light direction basically prescribes an outgoing light direction that is a reflected direction from another surface. Like when light falls onto the surface right here, that means it has to come from somewhere else, right? And light can be reflected off of other surfaces, like this surface here, right? And in order to compute the light that is coming from the surface, we have to do the very same thing that we're doing for this surface. We have to do it again for this surface. Like we again have a point of interest, and we have an outgoing light direction. Like those light directions now switch roles. Like for this surface, the light direction is actually omega O, while with regards to this point here, the light direction is omega I, right? And then this prescribes another incoming light direction. And then we potentially have another surface, right? So that means we basically have a recursive function here. The light transport equation is a recursive function, and even more so, we're even integrating all possible light directions. Like we're really interested in over the hemisphere above the surface point that we're interested in. We have to evaluate all possible light directions, and those possible light directions have a statistical probability associated with them. Like the BRDF will tell us that certain light directions are impossible, and other light directions are more likely to contribute light. So the BRDF will tell us certain things about the probability of light coming from one of those directions. But generally, we have to evaluate reflected lights from all over the hemisphere above the surface. So this should illustrate the complexity of the light transport equation. So one term that we haven't discussed so far is we never discussed where light originally comes from, and that's what this term LE is for. Like the LE term basically says that there are some surfaces that can actively emit light. Like the surfaces that we discussed so far, the reflecting surfaces are passive in that they just reflect light. And we are assuming that there are some surfaces that can actually emit light. So light has to come from somewhere. And like in general, like this equation assumes that there's a certain percentage, to which the surface is emissive, and another certain percentage to which the surface is reflective. Yeah, and the very last term that we'll discuss is the so-called cosine term. And the cosine term can be thought of as a percentage of light arriving at the surface patch. And the cosine term is just proportional to the angle of this vector omega I here and another vector that is perpendicular to the surface at the position x. And so the cosine term is proportional to the cosine of that angle. That means, as we're dealing with unit vectors here, this is basically a dot product. So, and if this dot product is like 1, that means we like the light shines on the surface right from above, and that means we have 100% light contribution. And the more the light actually grazes, the less light actually arrives at the surface patch. Like in the end, when we're almost at a 90-degree angle, then the light contribution is near 0%. So I mean, this can be a real showstopper, right? Because we've done all that computation, like we computed the BRDF, but also we've potentially also done this this very deep recursion where we have followed like lots of those paths, and then in the end we might find out that right here the light contribution cancels completely because the light just grazes, right? And this can actually be a real showstopper for our computation and adds to the complexity of the light transport equation. And that should provide us with enough intuition to understand the light transport equation, at least to the degree that we need to understand it for this lecture. So the light transport equation tells us the light intensity, or the radiance, that is reflected into direction omega O from surface point x. And in order to determine this, the light reflected off of surface point x, we have to integrate over the whole hemisphere above x and recursively determine light from all possible incoming light directions and from all potential surfaces that reflect light into the direction of x. And with that understanding, like the equation is a huge recursive integral, we should be able to fathom the complexity of the light transport equation. And the solution to the light transport equation that we will discuss, like all practical solutions to the light transport equation, are approximations. And we will, in the following, discuss several rendering algorithms, which are all approximations to the light transport equation, and they approximate the LTE to a different degree. Here, let me rush over some basic concepts real quick. Like when we're talking about objects, we make the simplifying assumption that we're only concentrating on opaque objects, so there's no light that can actually enter the object. And we're also assuming that the objects are inside a vacuum. And therefore, we can concentrate on this infinitesimal transition between object and vacuum, and we can model that as a surface that is represented with polygons. Polygons can be rather arbitrary, like there are convex or concave polygons, and we will in general assume that those polygons are themselves represented with triangles, as triangles basically allow us to tessellate any other convex or concave polygon. Here, and triangles actually allow us to represent relatively complex structures, and those structures we'll colloquially refer to as triangle meshes. So, and apart from triangle meshes and polygons, there's another important concept. Like when we're talking triangles, those triangles are made up of vertex positions, so 3D positions in space. And there's also associated with each triangle or each surface, there's something called a normal vector or a surface normal vector. And they're like a base primitive in computer graphics. They're used for lighting calculations, for visibility tests, but also for all sorts of other things. And what they basically are, they are a vector that is perpendicular to the surface. You can simply, like when you have a triangle, you can simply compute the surface normal by computing the cross product of two edges of the triangle. And those normal vectors allow for very simple, I will like colloquially refer to those as dot product operations. Like for instance, consider we have like a bunch of unit vectors, and we have a unit vector, let's call it V, and this is a unit vector that is pointing from a surface point, like the surface point X that we discussed for the LTE earlier, and the vector V points towards the viewer. And let's also consider that there is a vector capital L, and that is a unit vector pointing towards a light source. For instance, if we have that normal vector, and the normal vector is denoted n here, and if the dot product of the normal vector and the vector to the light source is below 0, then we know that the light source lights up the object from behind. When we're in a setting with opaque objects, like we agreed upon that we are, then we don't have to perform the lighting calculations. And then simple lighting models, like we discussed BRDFs earlier, and there are actually quite complicated BRDFs that assume like a complicated roughness and other complicated phenomena where the lighting is view dependent, and the most simple lighting models actually just assume that the light that is reflected off of the surface from point X is proportional to the angle between the normal vector and the light source. Yeah, so that basically means when the angle between normal vector and light source is exactly 0, then we have 100% light contribution. And when the angle approaches 90 degrees, like we have a grazing light angle, the light contribution is 0. And in between, we basically just interpolate. And this is another very simple dot product relationship, or a relationship that can be very easily modeled with a dot product. And similarly, like when we have a vector to the current camera position, based on the normal vector, we can decide if we view the surface from the front or from behind. When we're in a setting where we have only opaque objects and we assume that we cannot move into those objects, then we can potentially exclude surfaces from rendering because we know that we're watching them from behind. This is something that we call backface culling. It's an important concept that we'll later need to understand on GPUs. And so those are surface normals. So in order to compute lighting, surfaces usually store at their vertices something that is called a shading normal or a per vertex normal. And per vertex normals are obtained by just interpolating the face normals of the adjacent faces. Like for every vertex that's in the scene, I compute the average of all the adjacent surface normals, summing them up, like I'm accumulating the adjacent surface normals, and then in the end I'm dividing by the number of adjacent surfaces, and this gives me like an average normal for each vertex, and that allows me to smoothly interpolate the normals across a surface. And with that, I can create the illusion that a surface that is flat and that is patchy is actually smooth. Important operations in computer graphics are affine, angle-preserving transformations, like, for example, movements, rotations, uniform and non-uniform scales. And those operations are generally used to animate either the scene geometry itself, where we earlier assumed the scene geometry would be static for simplicity, but those transformations can also be used to move the viewing position and to adapt the viewing orientation, which we colloquially will refer to as the virtual camera. Again, the virtual camera can also be subject to transformations, and those transformations are realized using so-called transformations in homogeneous coordinates. And those homogeneous coordinates imply that points or vectors are 4D. So when we'll discuss those homogeneous transforms in a reasonable brevity, and just to give you an understanding, so a formal derivation or a longer discussion of this topic is way out of scope for this lecture, but it's such an important topic that we at least have to know what's going on there. There are the aforementioned transformations, like uniform or non-uniform scale, and a non-uniform scale matrix would look like the identity matrix, like the 4x4 identity matrix, only that the 0, 0, 1, 1, and 2, 2 diagonal entries would contain the scaling factors. Like, if we had a uniform scale, then those would just be the same. Then we have rotation matrices, which have a upper left 3x3 matrix, which contains the elements that are required for the transformation, and where the bottom row and the rightmost column are the 0, 0, 0, 1 vector. Then we have translations, where we have a 3x3 matrix that is just the identity matrix, and the bottom vector would be 0, 0, 0, 1. And then we have the translation just in the rightmost column. Like for the x-axis, for the y-axis, for the z-axis, we have the respective translation factors. So, and then what we can do with those transformation matrices, we can arbitrarily concatenate them. Like, given one of those transformations, one of those affine transformations, we can just, when there's another movement of the object, we can just accumulate this movement on top of the current transformation matrix by just performing a matrix-matrix multiplication. Yeah? And we can perform an arbitrary number of those, and by this just accumulating those matrices. So given these matrices, what they express is a sequence of transformations over time. And we can apply those transformations. And we can apply those transformations to three-dimensional points. And those three-dimensional points and homogeneous coordinates are given as column vectors with an x, y, and z coordinate that correspond to the point, and with a fourth, with a so-called w coordinate that is 1. And then in order to perform the transformation, we just perform a matrix vector multiplication. Likewise, we can also transform vectors, and the exception here is that the column vector that we construct consists of the x, y, and z component of the original vector, and the w component is 0. And then we can perform the same matrix vector multiplication in order to obtain the transformed point. So on a side note, if we were to transform normals, and without a formal derivation, I just want to mention that those are transformed differently. So they aren't transformed like vectors are transformed, but they are rather transformed as follows. So they aren't transformed in homogeneous coordinates at all, but normals would be transformed as ordinary 3D vectors. And those vectors are transformed by given the original transform, taking the upper left 3x3 matrix. Like this here is the upper 3x3 matrix, and then taking the inverse transform of that matrix. And given the inverse transform of that upper left 3x3 matrix, if we perform a matrix vector multiplication with that, that gives us our transformed normal. So I will not provide a formal derivation of this here, but this is the way that people transform normals in computer graphics. Yeah, and as I said, in the following, we will assume that the geometry is static, and therefore we'll now only concentrate on transformations that are applied to the camera. And those affine transformations allow us to move the virtual camera arbitrarily, like with the transformations. We're able to move the camera in space using a translation matrix, and we're able to orient the camera arbitrarily by applying a rotation matrix. And those transformations in regard to the camera are called, or what we are modifying here are the extrinsic parameters of the camera. So generally, what we're referring to here are the so-called model and viewing transformations. And the model transformations are the affine transformations that are applied to the geometry and to the objects in the three-dimensional scene. And the viewing transformations are the ones that are applied to the camera. And those together form the so-called model and viewing transformation. And as we're only concentrating on static geometry here, for us the model view and the viewing transformation are equivalent. So what we'll discuss next is the so-called perspective transformation, and the perspective transformation describes how to transform objects from world space into window coordinates so that we can draw them to the screen. And our description will roughly follow what the graphics APIs like OpenGL or Direct3D do, so that we're, with our description of this, are relatively close to the actual hardware. And the very first thing that I'm going to describe is the so-called visible camera frustum. So the visible camera frustum helps us to achieve perspective in a sense that objects that are closer by appear bigger than objects that are farther away. And the visible frustum is defined in terms of an aperture angle, and the aperture angle determines the field of view. And then the visible frustum is defined by two planes, by the z near plane and by the z far plane. And the objects that are inside the visible frustum are visible, and objects that are outside the visible frustum get clipped. So there is another 4x4 matrix, the so-called projection matrix, that is concerned with transforming vertex positions inside the visible frustum from world coordinates into the unit cube and eventually into window coordinates. And we will now very briefly discuss how one constructs that projection matrix. And in order to construct the projection matrix, we will just consider the various transformations that vertex positions will undergo when they are subjected to this transformation. And the very first transformation that happens, and that is just applied to all vertex positions, is one where we transform from so-called world coordinates to camera coordinates or eye coordinates. And the camera coordinate system is just a coordinate system where the camera position is at the origin, at the 3D position 0, 0, 0, and we're viewing along the negative z-axis. So this is a convention that holds true for instance, for OpenGL. And this is basically just an affine transformation that is happening here, that just moves the camera towards the origin and orients the camera in a way so that we're looking down negative z. So the next transformation will transform camera coordinates into orthographic coordinates. This transformation allows us to easily clip vertices against the various planes of the frustum. So, and as you can see, this transformation is not an affine transformation anymore, because it transforms the vertices from a perspective frame of reference to a orthographic frame of reference, where the clip planes are perpendicular to each other and form 90-degree angles. And the next transformation goes from those orthographic coordinates to so-called normalized device coordinates, or NDC, and those basically transform arbitrary length sides of the geometry that is induced by the clip planes to the unit cube, where edges and sides have length too. Depending on the API that we're in, OpenGL, Vulkan, and Direct3D handle this a bit differently. The orientation of the various sites might be different, but the frame of reference is one where the sites have length 2 and go from -1 to 1. So, and our final transformation is the so-called viewport transformation, which sees us going from normalized device coordinates to so-called window coordinates or screen coordinates. And this coordinate system is actually not a 3D coordinate system anymore, but a 2.5D coordinate system. What does that mean? That means that we essentially now identify our vertices using 2D positions and a depth. And depending on the API we're in, the coordinate system's origin is either in the bottom left corner or in the top left corner. Like in OpenGL, we have the bottom left corner, and in Direct3D and in Vulkan, the corner is the top left corner. And this coordinate system is actually the one where the raster engines that we will later discuss operate in and transform the 3D primitives into actual 2D projections. So, and there are several reasons why we go through all those transformations. Like on the one hand, there are a bunch of different coordinate systems, and there are also a bunch of different operations that are applied to the vertices, like certain visibility operations, like clipping operations, and so forth. And some of these operations are actually easier to perform in a certain coordinate system, like certain operations on normals or with regards to lighting are easier to perform in the camera coordinate system than in the world space coordinate system. And the transformation to orthographic coordinates and to a orthographic frame of reference, as the normalized device coordinates are, as also the window coordinates are, makes it much simpler to, in the end, project our primitives to the image plane, because there we have an exact correspondence between vertex positions, which are 2D, and positions on the image plane. Our discussion of the camera transformation was, of course, very simplified and really abbreviated, so in order to fit this into like a couple of slides, and in a real computer graphics lecture, there would be an in-depth discussion, and the perspective transform alone would probably fill a whole session. Apart from that, there are some important takeaways for us, and the important takeaways here are that the camera transform in general consists of two transformations, and one transformation is the perspective transformation, and the other one is the viewing transformation. And the viewing transformation changes every time when the camera moves, and this actually happens much more often than changes to the intrinsic camera parameters. Those quite often only change in the very beginning, like when the virtual camera is initialized. And the parameters that are influenced by the perspective transformation are the so-called intrinsic camera parameters, while the parameters like orientation and position of the camera are called the extrinsic camera parameters. And what is also important to note is that all those transformations can be expressed as 4x4 matrices and as matrix vector multiplications in so-called homogeneous coordinates. So the next thing that we have to worry about, now that we know how to transform our primitives into window coordinates, is how to actually project them onto the 2D raster. And the methods that come into play here are called scan conversion methods or scan conversion algorithms. And There's actually a bunch of different scan conversion algorithms. Like there are different algorithms for different types of primitives. But even assuming that we have triangles and polygons, there's a bunch of different algorithms that achieve this task. And one way to achieve that task is actually to first just rasterize the edges, and then just fill in the pixel positions in between. And algorithms that are often used in order to rasterize the edges are, for instance, DDA or Brassenham algorithm. So just to provide you with an intuition here, or like those algorithms basically work by like you are at a certain raster position and you know the line that you're rasterizing. Like you know the slope of the line, and then when you're going right, you have to make a decision if you're just going right or if you're also going up. And then you're making that decision, and then you continue the iteration, so to say, yeah. So and then you're at the next raster position, and then you make that same decision again, and then you do this like a bunch of times, and then eventually you have rasterized your line. So this is really just to give you an intuition, as the DDA and the Brassenham algorithms are the topic of a typical computer graphics 1 class, and there they are taught in depth. So they are not really relevant to our lecture, and in particular, they are not so relevant to our lecture because they are actually kind of hard to parallelize. Like they are algorithms that are actually widely taught in computer graphics classes, but they actually don't lend themselves very well to parallelization because they have this inherent iteration in them. Like you're at a certain position, and then you have to make a decision if you're going right or if you're going up, and only then you can process the next raster position. Yeah, so you have this inherent data dependency in there, and that makes those algorithms particularly hard to implement. And we're going to, in the next session, discuss an algorithm, the algorithm by Pineda. And this is actually a widely implemented algorithm, and most of the GPU vendors incorporate this algorithm in their raster engines that are responsible for projecting triangles onto the pixel raster. And this algorithm is basically based on computing signed areas of triangles, and we will discuss in our next session how that works in detail.